Okay, it's really nice to see a lot of young people in the audience. The talk is meant for everybody, and it's a little bit of the work that me, along with my colleagues and members of our lab, are involved in RLI with tremendous support from ISRO. So thanks once again also to Girish who's here from ISRO. So let's get started. So the name of the experiment that I'm going to talk about today is called Pratyush. Okay. Have any of you heard the word Pratyusha or Pratyush, or any of your friends, family, relatives, anyone called Pratyusha? It's a common name, at least that I know of. Yeah? Do any of you know what it means? No? Okay. It means the light from the dawn, the first light from the sun. Okay? So this is a very intentional name that we have chosen for this experiment because, like the meaning of the word, what this experiment is trying to do is try to detect the light from the very first stars that ever formed in our universe. Okay, so we are calling this experiment Pratyush. You may realize very soon, if you've been attending astronomy talks, that almost every word is an acronym. I'll tell you the acronym later, but this name was chosen for that reason. Okay. So before I move on, this is a picture of our team. It's not very up to date. There are 2 people, including in the audience here, whose headshots we have not yet gone, but. I'm part of the lab at the Raman Research Institute called the CMB Distortion Lab, and it's a mixture of people from various backgrounds, engineers, astronomers, PhD students, research assistants who just finished their bachelor's, but that's our group, and we also get tremendous support from various other groups at RLI, including the mechanical, electrical, the observatory that we have. So if you don't know that there is an observatory 80 kilometers from here, a radio astronomy observatory, come talk to us, we'll tell you about it, we'll go visit. Okay. So, I put all the numbers here, need not be a quiz, but let's do some logical reasoning, okay. We have measurements and theory that tells us that our universe today is about 13.8 billion years old. Okay. We also have an estimate that our sun is about 5 billion years old. So what is the first thing that comes to your mind? The sun and our universe are not the same age, which means the sun was born at some point. Okay? So let's think a little beyond that. How old is the oldest star that we know of in our universe? We have measurements that tells us it's about 13 billion years old. So even that is not as old as our universe. So the universe and the stars in the universe were not born at the same time. The very first stars in the universe turned on at some point. Okay? So we want to understand how this happened. Okay? So anyone in the audience want to take a guess how we know the age of a star? The clue is stars are factories that burn hydrogen and helium through nuclear fusion. Okay? So if you take a look at how much helium there is in a star, you can tell how old a star is. Okay, that's the first step. Of course, we use more advanced tools, but that's a general idea. So this gives us some information that stars were born at some point in the universe. So I'll walk you through very quickly about the current best understanding of our universe, the scientific understanding. We don't know exactly when or why or how it happened, but at some point the universe was created. What we call as Big Bang in popular language. For the first few minutes, within the first few minutes, the first atoms in the universe formed. Okay, the protons, electrons, helium nuclei in the universe are formed in the first few minutes. Okay, within about 100,000 years. Remember, the grand scheme of things, this is nothing. The universe is billions of years old. So when the universe was still a baby, the very first atoms formed. Most of these atoms are hydrogen atoms. The universe is mostly filled with hydrogen. Okay? For a long time, nothing really happened. I've still not told you about stars or galaxies. But today, when you look up at the night sky, you see stars and galaxies. At some point, they form too. Okay? This period, when the very first stars and galaxies form, is called as the cosmic dawn. Okay? And it is this period that we are interested in studying. So today, the universe is very evolved. There are stars and galaxies everywhere. Okay? We are trying to look back in time to look at those first stars and galaxies. So how do we go about looking further behind or looking at those first stars and galaxies? One thing we can do is to build ever bigger telescopes. You've heard of James Webb, right? You can make a very big optical telescope and try to take a photo of that very first star. Okay? But that's very hard due to technical reasons and also because how do you know that that star is bright in optical light? What if that star is not like our sun? Right? What if that star does not shine the same way like our sun shines or the other stars in today's universe shine? Right? We don't know if those stars are special or different. For this, we use another element in the universe. Okay? We use hydrogen. I just told you that hydrogen is the most abundant element in the universe. Okay? So don't think about what you see around yourself in Earth. Think of the universe as a much bigger place. On average, the universe is actually filled with hydrogen. Okay, we are the exception. We are not the norm. Okay, so that's what we do. We are going to try to study the early universe and deduce how, when the first stars formed using the signal from hydrogen. Okay, so hydrogen is a nice element. It's very simple. It has one proton and one electron. Okay, for the very young kids in the audience, proton is something we call positive. Electron is something we call negative. Okay, but hydrogen can exist in different states. Okay, you can have a proton and electron spinning the same way or spinning the opposite way. Okay, when a hydrogen atom goes from spinning the same way to spinning the opposite way, it emits a radio photon. It emits light. But this light is not the light you see with your eyes. It is light in the radio wavelength, like your FM that you listen to. That is also light. It is just that light you cannot see. Okay, it's radio in wavelength. So hydrogen emits a signal in the radio wavelength. And if you look at the hydrogen atom today on Earth at home, and it emits this photon, that wavelength is at something called 1420 megahertz, 1.4 gigahertz. Gigahertz is the frequency range in which maybe your mobile phone operates. Okay? But remember that the hydrogen signal we are trying to look for is from the early universe. It is not from Earth. It's not from a lab on Earth. Okay? The hydrogen signal we are trying to look for comes from the early universe. So what happens is this light gets stretched out. So by the time you receive it, you no longer receive it at your mobile phone wavelength. You receive it at your radio wavelength, FM wavelength. Okay? So that's typically what we call 100 megahertz or so. Okay? What we are trying to do at RRI is to build very sensitive radio telescopes that are trying to detect this signal from hydrogen from the early universe in this frequency range of 100 megahertz or so. This is not easy. Okay? This has never been detected by anybody in the world. Okay? The reason why this is challenging is that this signal we are trying to detect from hydrogen is 1,000,000 times weaker than the radio signal that comes from our own galaxy. Okay? Our galaxy is also a radio transmitter. It transmits at all frequencies, including at radio frequencies, and is very bright at radio frequencies. Okay? So 1 part in 1,000,000 is something like you're trying to find one drop of water in a few buckets of water. That is how hard this problem is. Okay? But not only is that the only problem, there are several other challenges. Before I move on, this is the type of signal we are trying to look for. Okay? You see there are many lines. Okay? Any one of those lines is the real signal that we think comes from the very first stars and galaxies. Specifically, this is the hydrogen signal in the universe during the time that the first stars and galaxies form. Okay? By detecting and understanding the signal, by finding the true signal, let's say you think it's this black one. Okay? If that black signal is the true signal of hydrogen from the early universe, that can tell us information about when exactly the first stars formed, okay? How they formed, what kind of light they emitted, okay? How did that light interact with the rest of the universe? How the next generation of stars and galaxies formed, and that brings us to an explanation of the universe we live in today. Okay, so it is an important problem, and that's a big open puzzle in current cosmology. We don't understand this. Okay? So I told you that our own galaxy is not the only problem. Okay? There are several other challenges to detecting this signal. Okay? A a few common things are, it's hard to build an experiment that is so clean, okay? If you're trying to detect something that is 1 part per million faint, you don't want your own instrument, your own detectors, your own receivers, your own antennas, that is something we can try to work on in the lab, okay? There are a few other things that are a challenge for us just because we are trying to detect the signal on Earth, okay? Some of these are, I mentioned, FM radio. So, anyone here listens to FM radio on your phone, car, anything? Yeah. So, the frequency range that we tune into is the name of the station, 94.3, right? 93.5, 101. They're all frequency ranges, and all of that is in 100 megahertz, 94.3 megahertz, 95 megahertz. And that is the same frequency range where our signal is sitting. So not only do we have a problem because our signal is so faint compared to our galaxy, on top of that, we as human beings are adding more noise. We are building FM stations, right? Another challenge is that when we try to do this experiment on Earth, there are two other problems. Our own ionosphere. Ionosphere is a layer in our atmosphere which is full of charged particles, and this can confuse our antenna, and it can introduce a shape in our data that may look like the signal that I detect. So we never know whether the signal we are seeing is coming from the early universe or something that our ionosphere is picking up. Similarly, our antenna, I'll show you a picture later. Our antenna is something that we take a lot of attention in designing. We want to make sure we do everything we can to not confuse the signal detection. Okay? But if you place that really beautifully designed and fabricated antenna on, let's say, soil, on this floor, the properties of the antenna will change. You can try to put this floor properties also into your design. But what about the layer of mud beneath it? What about that car parking structure beneath it? Right? So there are also challenges in terms of how well you can operate this experiment just by putting it on a surface. The solution is you go to the best place accessible to humankind today where none of these problems exist. You can go to the far side of the moon. Okay? When you look at the moon, have you noticed that it's the same face of the moon you see every single night when you see the moon? The moon is what we call tidally locked to Earth. We always see the same face of the moon. But then the moon is a lithosphere, kind of. And behind the moon is a place that we never see from Earth. And that is where we want to send our satellite. Okay, we want to send our experiment Prakash. The reason being that we have done radio studies, there have been simulations that tell us that the moon behaves like a signal jammer. You sit in this building and let's say there's a lot of concrete and your phone network is very poor. You step up and immediately everything is better. The moon does that to radio signals from Earth. I can tell you that if you get a nice trip to the moon, take it, you can receive FM radio on the near side. The side that you can see from Earth, you can receive FM radio there. But if you go on the far side, behind the moon, you're not able to receive that FM radio because the moon cuts it out, it blocks it. So when you put a satellite in orbit around the moon, you have solved three problems. One, you are behind the moon, so no FM radio. Two, the moon has no ionosphere to speak of. And three, you're orbiting, you're not sitting on any surface, you're in free space. So your antenna behaves exactly how you have simulated it, how you have tested it in physics. Which is exactly why they proposed this experiment called Prakash to ISRO headquarters in an announcement of opportunity for space payloads in 2018. Prakash has been in study phase, seed finding stage, and we have been approved by technical review committee and we are awaiting the next stage of review to go to project phase. So Prakash, as you can see, is this part. This is our experiment. I'll tell you a bit more about this structure later. So the idea is that there will be a dedicated craft with our antenna and electronics orbiting around the moon. When it is on the far side of the moon, when the moon is blocking both the Earth and the Sun, and it's completely dark both in optical and in radio, all the signals that this experiment will receive are from deep space, from the universe, from our galaxy. And that is something that we can deal with. Dealing with FM, dealing with ionosphere is harder. Okay? And when it comes to the near side of the moon, it will downlink and transmit the data. Here's a quick summary. So Pratyush is an experiment that is operating between 55 to 110 megahertz. That acronym I told you is written there, probing the reionization of the universe using signal from hydrogen. I like the poetic meaning better, which means signal from the first light of the sun. And we have proposed this in two stages. The first stage will operate around Earth. When you're operating around Earth, yes, you will still see FM, but you can be above most of the ionosphere and in free space. So we address some of the problems. And then eventually we want to go to phase 2 where we see the lunar orbit. This gray structure you see here is the Pratyush antenna. I have a mini model here, I can pass it around. This is what Pratyush will look like. Okay, so this is not like any conventional antenna you've seen. The reason being we have designed it specifically to not confuse our signal in the frequency range that we are trying to play the signal. And all our electronics, including payload electronics, spacecraft electronics, everything sit in what we call a satellite bus in this kind of rectangular box below. This is the current status of Pratyush. We have a laboratory engineering model working. It has been taking data. We have constantly been demonstrating that our receiver electronics in this stage with commercial components is capable of signal detection. What we have to work on next is to go to space-based components, move to project mode and get a launch. We still have a long way, but we are confident that when Pratyush flies, we will be able to detect the signals from the universe. And this picture here tells you that everything in blue are the types of signals that are predicted by theory that Pratyush can detect in Earth orbit. And the combination of both red and blue are the types of signals. So basically almost everything is what Pratyush will be able to detect with high confidence when it is orbiting around the moon on the far side. Okay, so I hope you got from this the kind of work that we have been doing at RLI. It is truly cutting edge. We are right across Native Circle here around Research Institute. So for those of you who have not been there, please contact us. We'll come and get a tour of the lab. We have very nice archival gallery and a lot of nice things to see there, so you can get a tour. And you also get a flavor of the kind of other research that